We'll start in 1 minute. In a few minutes, we'll continue with the test one review sheet. Later today, I will send an invitation for a Zoom meeting at 10 a.m. tomorrow for a short orientation about what we're going to do on for test one. So test one will be Zoom proctored on Friday, starting at about 10. Okay, we'll continue with the review sheet on part F. We have the indefinite integral of cosine of x squared times sine of x to the fourth dx. So I'll do a few steps on this one. We can think of this as the integral of cosine of x squared times sine of x squared times sine of x squared. And then we'll use identities for cosine of x squared and sine of x squared. So in particular, for cosine of x squared, 1/2 times the quantity 1 plus cosine of 2x. And for each of the sine of x squareds, we'll have 1/2 times the quantity 1 minus cosine of 2x. So we have three factors that we can multiply together, three constant factors. 1/2 times 1/2 times 1/2, which is 1/8. So I'll bring the constant factor 1/8 out front. Notice what we're going to get when we multiply 1 plus cosine of 2x times 1 minus cosine of 2x. That will become 1 minus cosine of 2x squared. And then we're multiplying that by 1 minus cosine of 2x. And 1 minus cosine of 2x squared is sine of 2x squared. So we'll write this as 1/8 times sine of 2x squared times 1 minus cosine of 2x. And from here, we'll write two separate integrals. One is 1/8 times sine of 2x squared. And the other one will be minus 1/8 times sine of 2x squared times cosine of 2x dx. Okay, I'll say a couple more things, but then leave the rest of this for you. You can replace sine of 2x squared with the quantity 1/2 minus 1/2 cosine of 4x using the same kind of identity that we already used before. And then that will be fairly simple to integrate after that. And then for the integral on the right, assign u to be sine of 2x, so that du is 2 times cosine of 2x dx. And then use the substitution rule to integrate this integral on the right. Okay, let's move on to the next one. Okay, part G, the indefinite integral of cosine of the natural log of x. So if we assign u to be the natural log of x, we're just using a substitution. U is the natural log of x, so du is 1 over x dx. And we'll write that as, for now, we'll write this as x times du equals dx. But we can replace x with an expression in terms of u. If u equals the natural log of x, then x equals e to the u. So replace this x with e to the u. And we get e to the u du equals dx. And from here we can transform this integral. So we'll have cosine of u, and then replace dx with e to the u du. Hey, we've seen integrals like this before, so I'll leave the rest of this for you to do. I'll just suggest that if you integrate by parts, so this one is going to be one of those sorts where you start by integrating this using integration by parts, and then you'll eventually have something involving subtraction of this, and then you'll have to add it to both sides, and then afterwards divide by whatever constant. So we've seen things like that before. Okay, let's move on to the next page. The indefinite integral of dx over x squared times the square root of x squared minus 36. So it looks like a trig substitution could work for this one. If we let x be 6 times secant of some other variable. We often use theta, but we shouldn't always expect to see theta. So I'll use a different variable this time. X equals 6 times secant of u. And so du is 6 times secant of u times tangent of u du. And x squared minus 36. Well, that's 36 secant of u squared minus 36. And that becomes 36 times tangent of u squared. Okay, so we can make substitutions in this integral. Oh, I fouled up here. This should be dx, not du. Dx is 6 times secant of u tangent of u du. So in the numerator, we'll replace dx with 6 times secant of u tangent of u du. Replace x squared with 36 secant of u squared. And then we're going to compute the square root of 36 tangent of u squared. So the square root of that is 6 times tangent of u. Hey, we get a bunch of cancellations. 6 divided by 6, tangent of u divided by tangent of u. And 1 factor of secant of u cancels. So we're going to get 1/36 times the indefinite integral of 1 over secant of u du. 1 over secant of u is cosine of u, so we get 1/36 times the integral of cosine of u du. And an integral of cosine of u is sine of u, and then plus a constant. Okay, we replace sine of u based upon our substitution up here. Since x equals 6 times secant of u, then x over 6 is equal to secant of u. So we use right triangle trigonometry. If this is the angle u, and if secant of u is x over 6, then the hypotenuse is x, and the adjacent side is 6. And the opposite side is the square root of x squared minus 36. And then sine of u is the square root of x squared minus 36 over x. So the integral is 1 over 36 times the square root of x squared minus 36 over x plus c. Okay, the next one, part I, the indefinite integral of tangent of x to the third times secant of x to the fourth. So we'll rewrite secant of x to the fourth as secant of x squared times secant of x squared. So we get tangent of x to the third times secant of x to the second times secant of x to the second dx. The middle secant of x squared, we'll convert that to tangent of x squared plus 1. And we'll leave the other secant of x squared the way it is. So we get tangent of x to the third times the quantity tangent of x to the second plus 1 times secant of x squared dx. And then you can distribute multiplication by tangent of x to the third. And then you can, after that, apply the substitution rule. If you let u be equal to tangent of x, then du is secant of x squared dx. And then it's pretty simple to integrate after those substitutions. So I'll leave the rest of this for you to do. Okay, in part J, we have the indefinite integral of dx over e to the x plus e to the negative x. Well, if we rewrite this in the denominator, e to the x plus e to the negative x is e to the x plus 1 over e to the x. And then if we have a common denominator of e to the x, we'll get dx over e to the 2x plus 1 over e to the x. And then we can simplify this complex fraction by writing this as the indefinite integral of e to the x dx over e to the 2x plus 1. Okay, so there's a fairly obvious substitution we can make if we assign u to be e to the x, and du will be e to the x dx. So we see e to the x dx in the numerator, so we will replace that with du. And in the denominator, replace e to the 2x with u to the second. So we have the integral of du over u to the second plus 1. So I've lost count how many times we've seen integrals like this. What's this integral equal to? Yeah, the inverse tangent of u plus a constant. And then we replace u with e to the x again. So we get inverse tangent of e to the x plus. Okay, and the next one, part k. The indefinite integral of 2 minus x over the square root of 4 plus x squared. For this one, I prefer to write it as a difference of two separate integrals. One will be 2 over the square root of 4 plus x squared dx. And the other one will be minus the integral of x over the square root of 4 plus x squared dx. Okay, so we can use a trig substitution for the left integral by assigning x to be 2 times tangent of theta, or just make sure that the variable you pick is different than x. And so dx will be 2 times secant of theta squared d theta. For the integral on the right, we could use the substitution rule if we let u be 4 plus x squared. So over here, u is 4 plus x squared, and du is 2x dx. So we already have the x, we just need to multiply by 1 in the form 1/2 times 2. And then use the substitution rule to evaluate that. Okay, so let's take these a couple of steps further. So I'll replace 2 times dx in the numerator. So we already have a factor of 2, and then multiply that by 2 times secant of theta squared d theta. Okay, and in the denominator, when we replace x with 2 times tangent of theta, we'll get 4 plus 4 times tangent of theta squared, which is 4 times secant of theta squared. And then when we take the square root of 4 times secant of theta squared, we get 2 times secant of theta. And we're going to get some cancellations on this one. But let's go ahead and work on the other integral on the right. So we multiply by 1 in the form 1/2 times 2. So we get 1/2. I'm going to write this as 2x. Since we have the square root of 4 plus x squared in the denominator, I'm going to write this as the quantity 4 plus x squared to the negative 1/2. And then we can just integrate this directly in the next step. Okay, so this integral on the left simplifies to 2 times the integral of secant of theta d theta. We might as well go ahead and evaluate this one. We get minus 1/2 times the quantity 4 plus x squared to the positive 1/2 divided by 1/2. And a little bit further. Okay, the antiderivative for secant of theta is the natural log of the absolute value of secant of theta plus tangent of theta. And this other one simplifies to minus the square root of 4 plus x squared, and then plus a constant. Hey, we have a little bit more work to do on this one. We have to replace secant of theta and tangent of theta with expressions in the variable x. So our original assignment, x equals 2 times tangent of theta. So where can I write that? So x over 2 is tangent of theta. Let's do the right triangle stuff up here. So if the angle is theta, and if tangent of theta is x over 2, then the hypotenuse is the square root of 4 plus x squared. So we get 2 times the natural log of, instead of secant of theta, we can write the square root of 4 plus x squared over 2. Plus x squared over 2, and then plus tangent of theta is plus x over 2. And then the other part is already done, minus the square root of 4 plus x squared plus a constant. If you can read that. Okay, the next page Part L, the indefinite integral of tangent of x plus secant of x dx. This is just a one-liner. The antiderivative, there's more than one way to write the antiderivative of tangent of x, but the most common one seems to be the natural log of the absolute value of secant of x. And then the antiderivative of secant of x is the natural log of secant of x plus tangent of x. And that's all there is to that one. Okay, in part M, so this one can take a lot of time, so I'll just set this one up. So I'm going to use W as my substitution variable, and I'm going to write W equals 1 plus 2x. So dW is equal to 2 times dx, or 1/2 dW equals dx. Okay, in the numerator, we have e to the 2x. So since W is assigned to be 1 plus 2x, then W minus 1 is equal to 2x. And we also have a factor of x in the numerator. So W minus 1 divided by 2 is equal to x. Okay, let's go ahead and make those substitutions. We're going to replace dx with 1/2 dw, so I'm going to bring the constant factor 1/2 out front. In the numerator, we'll replace x with w minus 1 over 2. And then instead of e to the 2x, we'll have e to the w minus 1. And in the denominator, we'll get w to the second, and then dw. Yeah, I'll just take this one a step or two further. We're going to focus on simplifying w minus 1 over 2 divided by w to the second. That's not too hard. That's just w minus 1 over 2 w to the second, and then times e to the w minus 1. And it might be convenient to rewrite w minus 1 over 2 times w to the second as a difference of two terms. So one will be w over 2w to the second, but that will simplify to 1 over 2w. And then the other one will be minus 1 over 2w to the second. And then we multiply that quantity by e to the w minus 1 dw. Okay, so this is as far as I'm going to take it. I'll just mention that now use integration by parts. So as you can see, you might want to write the difference of two separate integrals and then use integration by parts on each of them separately. So this could take us quite a few minutes if we work this out. So I'll leave the rest of that for you to work on. This is sort of advanced. If you get stuck, don't be extremely worried about it. Okay, the next problem, the indefinite integral of x squared over the square root of 25 minus x squared dx. Hey, this one looks like a trigonometric substitution might get us somewhere. So since we have in the denominator the square root of 25 minus x squared, so we'll try x equals 5 times sine of some variable like u or theta or something other than x. So if x is 5 times sine of u, dx is 5 times cosine of u du. And 25 minus x squared is 25 minus 25 sine of u squared. But using a Pythagorean identity, this becomes 25 times cosine of u squared. So let's make substitutions. So in the numerator, x squared will be replaced with 25 times sine of u squared. And in the denominator, the square root of 25 minus x squared is equivalent to the square root of 25 cosine of u squared, which will be 5 times cosine of u. And then never forget dx. dx is 5 times cosine of u du. Okay, the 5 times cosine of u divided by 5 times cosine of u cancels or equals 1. And then we have a constant of 25 multiplied by the indefinite integral of sine of u squared. Remember that sine of u squared can be written as 1/2 times the quantity 1 minus cosine of 2u. And we have a fairly simple integral to evaluate. We have this constant 25 times 1/2, so I'll bring the constant 25 halves out front. And then when we integrate 1 minus cosine of 2u, we'll get u minus 1/2 times sine of 2u. Okay, then we have to replace u with some expression in terms of x. Well, since x equals 5 times sine of u, so I'll use different ink. X over 5, x divided by 5 equals sine of u. So that means u is equal to inverse sine of x divided by 5. Okay, that's going to take care of that u. What about sine of 2u? So this works out pretty nicely. Minus 1/2 times sine of 2u. So sine of 2u is equal to 2 times sine of u times cosine of u. So 1/2 times 2 times sine of u times cosine of u, we'll just get minus sine of u times cosine of u. So the identity I used for sine of 2u, again, sine of 2u is 2 times sine of u times cosine of u. That's a very handy identity to remember. Okay, then we need to replace sine of u with x over 5. That was convenient. And then cosine of u, well, let's use a right triangle to help us. So if this angle is u and sine of u is x over 5, then the adjacent side is the square root of 25 minus x squared. And so cosine of u will be the square root of 25 minus x squared over 5. Okay, I'll leave the rest of that for you to do since I'm about out of space. Just use this. I'll just mention sine of u is x over 5. Cosine of u is square root of 25 minus x squared over 5. And you're multiplying those. Okay, the next one, the integral of cosine of 7x times sine of 3x dx. I didn't leave a lot of space on this one. So on a separate piece of paper, I'll remind you of a couple of trig identities that we can use for this one. So in particular, sine of a plus b, this is sine of a times cosine of b plus cosine of a times sine of b. And then the conjugate sine of a minus b is sine of a times cosine of b minus cosine of a times sine of b. So on part O, the integrand is cosine of 7x times sine of x. So the integrand has this form, cosine of a times sine of b. So if we subtract the bottom equation from the top equation, we'll get sine of a plus b minus sine of a minus b. These first two terms cancel each other out upon subtracting, and the other one, we're combining like terms, but we're subtracting a negative, so we're going to get 2 times cosine of a times sine of b. So the identity that we want is cosine of a times sine of b equals this quantity divided by 2, sine of a plus b minus sine of a minus b, all divided by 2. Okay, so if we, for this one, if we remember that identity, or you can I'll see if I can make it visible at the same time we're going to use it. So you might be able to see that. Okay, so we'll transform this integral to the integral. I'll bring the factor 1/2 out front. And then instead of a, we have 7x, and instead of b, we have 3x. So we have sine of 10x, and then minus sine of 7x minus 3x, sine of 4x dx. And this is pretty simple to evaluate. So we get 1/2, and then let's see, this is this is going to be negative 1/10 times cosine of 10x. And over here, we're going to be subtracting a negative, so it's going to be plus 1/4 times cosine of 4x. And so on. You can simplify a little bit more if you want. Okay, let's move on to the next part. Okay, so on these, convert the following integrals into integrals in powers of trigonometric functions by using trigonometric substitutions. Do not attempt to evaluate the resulting integrals. So let's not spend a lot of time since time is running out. We see in the denominator x squared minus 4 raised to the 3/2. So the trig substitution we want for that is x equals 2 times secant of theta. And so dx will be 2 times secant of theta tangent of theta. I'm not using u, but up here they refer to those as functions of u, but that's okay. Okay, so we'll just take this one step further. X squared is 4 times secant of theta squared. In the denominator, x squared minus 4, that's 4 secant of theta squared minus 4, which is 4 times tangent of theta squared. So when we raise that to the 3/2 power, it's going to turn out to be 8 times tangent of theta to the 3rd, and then times dx is 2 times secant of theta tangent of theta. We can simplify a little bit more, but let's leave it like this for now. Okay, and the next one, part B, the integral of x to the 3rd times x squared plus 9 to the 3/2 dx. So we see the expression x squared plus 9 raised to the 3/2. So this time we'll assign x to be 3 times tangent of u, and dx is 3 times secant of u squared du. So the x squared plus 9 is 9 times tangent of u squared plus 9. That simplifies using the identity 9 times secant of u squared. So replace x to the 3rd with 27 times tangent of u to the third. And then if we raise something to the 3/2, first take the square root and then raise it to the third power. So when we do that, we're going to get 27 times secant of u to the third, and then multiply all of that by dx, which is 3 times secant of u squared du. So we won't evaluate that one. Okay, the next one, part C. So on this one, we need to do some preliminary work in the denominator. Inside the square root, we have 4 plus 2x minus x squared. And we're going to complete the square on the x squared term and the x term. So we'll think of this as 4 minus the quantity x squared minus 2x. And then we're going to add 0, but on the inside of the parentheses, we'll complete the square. Okay, so we take half of -2 and square it, which is +1. But by writing +1, we've actually subtracted 1. So to compensate for that, we add 1 on the outside. See how that works? And then the 4 plus 1 becomes 5, and then minus this quantity squared, which is x minus 1. This quantity x squared minus 2x plus 1 is equivalent to the quantity x minus 1 squared. Okay, then from here, we could use a substitution. So this time we'll write x minus 1 equals the square root of 5 times sine of some other variable besides x. So I'll use theta. And so dx will be the square root of 5 times cosine of theta d theta. Okay, so inside the square root, in the denominator, the square root of 4 plus 2x minus x squared is equivalent to 5 minus the quantity x minus 1 squared. And when we make substitutions into that, we're going to get, this is going to simplify to 5 times cosine of theta squared. And that's going to go inside the square root. So we'll take this a step further. Since x minus 1 is the square root of 5 times sine of theta, x will be the square root of 5 times sine of theta plus 1. And in the denominator, we're going to take the square root of 5 times cosine of theta squared. So that's going to be the square root of 5 times cosine of theta. And then our dx is the square root of 5 times cosine of theta d theta. So that's as far as we'll take that one. Okay, we have less than 2 minutes left. So deriving formulas for these aren't too bad, really. The indefinite integral of the natural log of x to the n, if we assign u to be the natural log of x, du is 1 over x dx. And so x times du equals dx. And we saw this earlier today. We can replace x with e to the u using this assignment here. So dx will be e to the u du. And then when you make substitutions, we'll get u to the n times e to the u du. To take this further, you would just use integration by parts. Okay, we're out of time. I will send the answers to the test one review sheet a little bit later today. And also later today, I'll send an email about the Zoom meeting that we will have tomorrow at 10, just for a few minutes to discuss Friday's test. But that's all for today. So go ahead and sign in for attendance.